Have you ever heard that saying, the more I learn, the more I realize how much I don't know?
Yeah.
Well, get ready to feel that way because today we're going to dive deep into how even the most basic ideas in physics had to be completely rethought.
Absolutely. And that's exactly what Einstein and Infeld set out to show us in their book, The Evolution of Physics.
Okay, so let's unpack this a little bit.
Yeah.
What kind of clues are we even talking about here? I
Right.
mean, physics can seem so, like, cut and dry. Like it's all figured out already.
Right.
So where do we even begin?
Well, let's start with something as basic as mass.
Okay.
You'd think that'd be pretty straightforward, right?
Yeah, how much stuff an object has.
Right, exactly.
Yeah.
But even that seemingly simple concept has like hidden depths.
Okay, hidden depths. I'm intrigued.
Well, Einstein and Infeld point out that there are actually two ways to define mass.
Okay.
You have inertial mass,
Okay.
which is an object's resistance to being moved.
Hmm.
And then you have gravitational mass, which dictates how strongly it's pulled by gravity.
So like a bowling ball has more inertial mass than a tennis ball because it's harder to get moving,
Exactly.
but it also has more gravitational mass because it's heavier.
Exactly.
Right.
Now, what's remarkable is that those two types of mass,
Yeah.
despite being defined so differently, always seem to be equal.
Huh.
Classical physics just kind of shrugged this off as a coincidence.
Uh-huh.
But
Here's where it gets interesting.
this is where it gets really interesting.
Right.
Einstein and Infeld saw this coincidence as a huge clue.
Okay.
They argued that the equivalence of inertial and gravitational mass
Yeah.
points to a deeper connection between gravity and acceleration,
Wow.
which is actually a core principle behind Einstein's theory of general relativity,
Okay.
which completely revolutionized our understanding of gravity.
So even something as basic as mass has these profound implications for understanding the universe.
Absolutely, and this is just the tip of the iceberg.
Right.
The evolution of physics takes us on this journey through centuries of scientific thought,
Okay.
showing how each new discovery kind of forced physicists to rethink their assumptions.
So if we're starting at the beginning,
Yeah,
does that mean we're going all the way back to like Aristotle and folks like that?
you got it.
Okay.
Einstein and Infeld actually start by comparing scientists to detectives,
Okay.
piecing together clues to solve the universe's greatest mysteries.
I like that.
Yeah,
And like a good detective story, sometimes the most obvious answers are wrong.
precisely.
Right.
For centuries, Aristotle's view of motion dominated.
Okay.
He thought force was needed to keep something moving.
Okay. So push a cart, it moves. Stop pushing, it stops.
Exactly. It seems intuitive.
Right. It makes sense.
Right.
But is that the full story?
That's not the full story.
Okay.
Galileo challenged this idea with his concept of inertia.
Okay.
He argued that objects naturally resist changes to their motion.
Okay.
So a moving object wants to keep moving in a straight line at the same speed, unless a force acts on it.
So like a hockey puck sliding across the ice.
Exactly.
It would keep going forever if there was no friction to slow it down.
Exactly. Friction is a force
Right.
that changes the puck's motion.
Okay.
And Newton later formalized this into his first law of motion,
Okay.
which states that an object at rest stays at rest and an object in motion stays in motion
Okay.
unless acted upon by a net force.
Which is a pretty big shift from Aristotle's idea that force is needed just to keep things moving.
Huge shift.
Yeah.
This shift in focus from speed to change in speed,
Okay.
what we call acceleration, was key to understanding how forces really work.
Okay.
And to describe this change, we need to go beyond just numbers. We need
Vectors.
Vector,
I remember
right.
those from high school physics.
Yeah,
They have both like magnitude and direction.
right, you got it.
Okay.
Velocity isn't just about how fast something is moving,
Right.
but also in what direction. And force, too, is a vector. The direction of the force determines the direction of the change in velocity.
So if you push that hockey puck north,
Mhm.
it will accelerate north.
Mm-hmm.
But if you push it east, it accelerates east, even if you push with the same strength.
Exactly. And just like we need vectors to describe motion in a straight line,
Yeah.
we need them to understand motion along a curve,
Right.
which, let's face it, is a lot more of what we see in the universe.
Okay, so I imagine things get a little more complicated with curves.
Yeah.
What did Einstein and Infeld have to say about that?
Well, they emphasize that the basic principles are still the same.
Okay.
They use the concept of a tangent,
Okay.
that line that grazes a curve at only one point,
Mm-hmm.
to show how to determine the velocity of an object moving along a curve.
So at any given moment, the object's velocity is in the direction of the tangent to the curve at its current location.
Precisely.
Okay.
And the force acting on the object will cause its velocity to change either in magnitude direction or both.
Gotcha. Can you give me an example of how this works in the real world?
Sure, think of a ball being thrown.
Okay.
Its path is curved because of gravity, right?
It goes up and then comes back down in an arc.
Even though the force of gravity is always pulling straight down,
Yeah.
the ball's velocity is constantly changing both in speed and direction as it moves along that curved path.
So even though gravity is acting in one direction, it's the combination of that force and the ball's initial velocity that creates the curved trajectory.
Exactly.
Okay.
That makes sense.
Or take something moving in a circle like a ball on a string. Yeah.
So the tension in the string is constantly pulling the ball inwards,
Yes.
keeping it from flying off in a straight line.
Exactly. A force, in this case the tension,
Yeah.
is always directed towards the center of the circle, causing the ball's velocity to constantly change direction,
Right.
thus keeping it moving in a circle.
So whether it's a ball flying through the air or whirling around on a string, the same basic principles of motion apply.
We're starting to see how physics connects the dots in the universe.
And remember, this is all building on that foundation laid by those detective physicists centuries ago, as Einstein and Infeld write.
Yeah.
The evolution of physics is a continuous process. Each new discovery is built upon the work of those who came before.
And sometimes those new discoveries completely overturn what we thought we knew.
That's right. In fact, there was a time when physicists thought that heat was a substance, a weightless fluid called caloric. Yeah, it might sound strange now.
Yeah.
But the caloric theory actually explained quite a bit.
Okay.
They thought heat flowed from hotter objects to colder ones.
Oh.
Kind of like how water seeks its own level.
So when you touch a hot stove, caloric flows into your hand, making you feel the burn.
That was the idea.
Okay.
But this theory ran into some serious problems.
Okay.
Especially when scientists started investigating how heat could be generated through friction.
Like rubbing two sticks together to make fire.
Exactly.
Yeah, the classic example.
That heat seemed to come out of nowhere.
Right.
Not from some existing caloric source.
Right.
One particularly damning experiment was done by Count Rumford,
Okay.
who noticed that boring cannons generated a tremendous amount of heat,
Wow.
seemingly without limit.
So you couldn't just say there was a finite amount of caloric stuff inside the cannon that was being released.
Exactly.
Yeah.
This challenged the whole idea of heat as a substance.
Right.
Instead, scientists started to think of it as a form of energy,
Okay.
just like mechanical energy.
Ah, so this is where we start getting into the laws of thermodynamics.
Right.
Energy can't be created or destroyed, just converted from one form to another.
Right on that's a huge turning point in physics.
Yeah.
It meant that heat, light, chemical energy,
Yeah.
they're all part of the same grand scheme.
Wow.
And it also led to the development of the concept of entropy.
Entropy. Okay.
Yeah.
I've always found that a little bit mind-boggling.
Yeah.
It has something to do with disorder, right?
You got it.
Yeah.
Entropy is a measure of how spread out energy is within a system.
Okay.
The more evenly spread out the energy, the higher the entropy.
Okay.
And one of the fundamental laws of thermodynamics states that in a closed system, entropy always tends to increase.
So things naturally move toward a state of greater disorder. Kind of like how my desk always ends up cluttered no matter how hard I try to keep it organized.
That's a great analogy.
Okay.
It's not that things are falling apart,
Yeah.
but rather that energy is becoming more evenly distributed,
Okay.
leading to a state of higher entropy.
So it's not necessarily a bad thing, it's just the way things work.
Exactly. It's just the natural order of things.
Okay.
Yeah.
It's amazing how these fundamental concepts of energy and entropy has such broad implications for our understanding of the universe.
Yeah, it's really fascinating.
But let's go back a bit.
Okay.
We were talking about heat.
Yeah,
And heat is related to light, right?
absolutely.
Didn't scientists also struggle to understand the nature of light itself?
Absolutely. The question of whether light was a wave or a particle puzzled physicists for centuries.
Really?
In fact, even figuring out that light had a speed at all was a huge breakthrough.
Wait, so people used to think light traveled instantaneously.
Yeah.
Like as soon as something happened, you could see it no matter how far away you were.
That was the prevailing view for a long time.
Wow.
Even Galileo, who was way ahead of his time in many ways,
Yeah.
couldn't measure the speed of light accurately.
All right.
He imagined an experiment where two people would signal each other with lanterns across a distance, but
light's just too fast to measure that way.
exactly. It
Right.
wasn't until centuries later that a French physicist named Hippolyte Fizeau
Okay.
came up with an ingenious method,
Oh.
using a rotating toothed wheel to make precise measurements.
A toothed wheel. How does that even work?
So imagine a beam of light passing through a gap between two teeth on a rapidly spinning wheel.
Okay.
As the wheel spins, the gap opens and closes, chopping the light beam into pulses. These pulses then travel to a distant mirror and reflect back toward the wheel.
So if the wheel spins at just the right speed, the returning pulse will pass through the next gap between the teeth.
Precisely.
Okay.
But if it's spinning slightly too slow or too fast, the pulse will hit a tooth and get blocked.
Gotcha.
By carefully measuring the distances and the speed of the wheel,
Yeah.
Fizeau was able to calculate the speed of light.
And what was the verdict? Just how fast is this stuff moving?
Well, his experiment and later refinements revealed that light travels at a staggering speed of approximately 299,792,458 meters per second.
Wow, that's almost 300,000 kilometers per second.
It is incredibly fast.
No wonder Galileo had trouble measuring it.
Right.
So knowing light has a finite speed.
Yeah.
What did that change about our understanding of the universe?
Well, for one thing, it meant that looking at distant objects is like looking back in time.
Oh.
The light we see from a star, for example,
Yeah.
left that star years or even centuries ago. The farther away something is, the further back in time we're seeing it.
So it's like the universe is a giant time machine.
Exactly. It's a fascinating concept.
But knowing light travels at a specific speed doesn't tell us what light is.
Right.
Back to that wave versus particle debate.
Right. There was Newton, who proposed a corpuscular theory, arguing that light was made of tiny particles, almost like bullets.
So he thought light was like a stream of these corpuscles flying through space.
Exactly. And this theory could explain things like reflection, with light particles bouncing off surfaces, like a ball bouncing off a wall.
Yeah.
But it had trouble explaining other phenomena.
Like what?
Like how light bends when it passes from air into water.
Right. Why would particles change direction like that unless something was acting on them?
Exactly. That was one of the challenges.
Didn't someone else propose an alternative theory?
Yes. Christian Huygens, a Dutch scientist,
Okay.
proposed a wave theory of light.
Cool.
He imagined light spreading out in waves. Okay.
Like ripples on a pond.
I like that.
And this theory could neatly explain both reflection and refraction.
Okay, so which one was right?
Yeah.
Was light a wave or particle?
It sounds like we need another one of those crucial experiments to settle the debate.
Right, exactly.
And it came in the form of Thomas Young's famous double-slit experiment.
Okay.
In 1801,
All right.
he shined a beam of light through two closely spaced slits.
Okay.
Now, if light was made of particles,
Yeah.
you'd expect to see two bright spots on a screen behind the slits.
Right, two beams of light passing through the slits.
Yeah, but that's not what happened.
That's not what happened. Okay.
Instead, Young observed a pattern of alternating bright and dark bands. On the screen, this is called an interference pattern.
Okay.
And it's a classic sign of wave behavior.
Interference. How does that work with light?
When two waves meet,
Yeah.
they can either reinforce each other, creating a brighter spot,
Okay.
or cancel each other out, creating a dark spot.
In Young's experiment, the bright bands were where the light waves from the two slits were reinforcing each other,
Okay.
and the dark bands were where they were canceling each other out.
So that pattern only makes sense if light is behaving like a wave.
Exactly.
It's like those ripple patterns you get when you drop two pebbles into a pond close together.
Exactly. A great analogy.
Okay, so case closed light is a wave.
Well, hold on to your hat because the story's not over yet.
Oh, no.
Enter James Clerk Maxwell,
Okay.
a brilliant Scottish physicist
All right.
who unified electricity and magnetism with his famous equations.
Okay, I think I remember him.
Yeah.
Didn't Maxwell's work also have something to do with light?
You're on the right track.
Okay.
Through his equations, Maxwell showed that electric and magnetic fields could actually propagate through space as waves.
As waves.
And when he calculated the speed of these electromagnetic waves, it turned out to be...
Forward, the speed of light.
Exactly. It was a truly mind-blowing realization. Light wasn't some separate phenomenon, but a specific type of electromagnetic wave.
Right.
It was a grand unification that went far beyond just explaining electricity and magnetism.
So light is just a tiny part of this much larger electromagnetic spectrum.
Precisely. Radio waves, microwaves, infrared, visible light, ultraviolet X-rays, gamma rays.
Wow.
They're all electromagnetic waves,
Okay.
differing only in their wavelengths.
It's like finding out that your whole life you've only been listening to one instrument in a giant orchestra.
That's a great way to put it.
Yeah.
And what's even more remarkable is that this revelation about light
Yeah.
also pointed towards the limitations of the mechanical view of the universe.
The one we talked about earlier that said everything could be explained by forces acting on particles.
Exactly.
But how did light challenge that view?
Remember those electromagnetic waves Maxwell described?
Yeah.
They could travel through a vacuum,
Yeah.
meaning empty space.
Right.
This completely contradicted the mechanical view, which required a medium like air or water for waves to travel.
So it's like realizing that sound can't travel in space because there's no air to carry the sound waves.
Exact.
But light, being an electromagnetic wave, doesn't need any medium at all.
Exactly.
Or-
This discovery was a major blow to the mechanical view,
Yeah.
paving the way for the revolutionary ideas of relativity and quantum mechanics,
Okay.
which would completely transform our understanding of the universe.
Yeah, it was a truly exciting time in physics.
Right.
The old certainties were crumbling,
Yeah.
and scientists were grappling with these strange new concepts that challenged everything they thought they knew.
So we've got light behaving as both a wave and a particle,
Right.
electromagnetic waves zipping through empty space.
Uh-huh.
Where did physics go from there? Did Einstein and Infeld have any thoughts on how to make sense of it all?
They did. In The Evolution of Physics, they emphasize that this period of upheaval ultimately led to two of the most revolutionary theories in modern physics.
Einstein's theory of relativity and the development of quantum mechanics.
Now, those are two big topics even for a deep dive.
Yeah, they are.
Could you give me like a quick rundown of what they're all about?
Sure. So Einstein's theory of relativity, in a nutshell, completely changed our understanding of space and time.
Okay.
It showed that those concepts weren't absolute, but relative to the observer's motion.
So time can actually pass at different rates for different observers.
Exactly. Sounds crazy.
Yeah.
But it's been experimentally verified countless times.
Wow.
And this has profound implications for our understanding of gravity cosmology and even the nature of reality itself.
Okay, that's mind-blowing enough as it is. What about quantum mechanics?
Yeah.
What's that all about?
So quantum mechanics delves into the world of the very small,
Okay.
the realm of atoms and subatomic particles. It revealed that at this level, energy comes in discrete packets or quantitae.
Okay.
And particles can behave like waves just like light.
So the world at the smallest scales is completely different from the world we experience every day.
It is in the quantum realm, things aren't so clear-cut.
Right.
Particles don't have definite positions or speeds, but rather exist in a state of probability.
Okay.
It's a world where uncertainty and randomness reign.
It's like the universe plays by a whole different set of rules down there.
Exactly. And as strange as those concepts might seem,
Yeah.
both relativity and quantum mechanics have been incredibly successful
Right.
in explaining a vast range of phenomena, from the behavior of black holes to the workings of transistors in our computers.
Wow.
Yeah.
It's amazing.
It's amazing to think that all this came out of questioning some basic assumptions about the nature of light and heat.
It really shows the power of scientific curiosity.
Right.
And as Einstein and Infeld point out,
Yeah.
this evolution of physics is far from over.
Oh, really?
They write, "The history of science teaches us that no theory can be considered as final."
So there's still mysteries out there waiting to be solved, new revolutions in physics waiting to happen.
Absolutely. The quest to understand the universe is a continuous journey.
And who knows what incredible discoveries lie ahead.
Well, I think this deep dive has given me a whole new appreciation for the elegance and the strangeness of the physical world.
Yeah, it's a fascinating subject.
And I'm definitely going to be thinking about those two types of mass next time I pick up a bowling ball.
That's great. I encourage our listener to do the same, look around at the world
Yeah.
with the newfound sense of wonder.
Right.
Ask questions, challenge assumptions, and never stop exploring the mysteries of the universe after all. As Einstein and Infeld so eloquently put it, the most beautiful experience we can have is the mysterious emotion. It is the fundamental emotion which stands at the cradle of true art and true science.